talk about van der Waals gas thermal expansion alpha versus T. So this is the type of problem where the algebra is complicated, but you could have done it intuitively, and it's actually nice. So let's work through this one. Thermal expansion alpha versus T. So this is for midterm. So we have two axes. We are talking about alpha versus T. And we are talking about what's van der Waals gas, which P is equal to nRT by V minus NB minus AN square by V square. Okay, very high temperature. How should a van der Waals gas behave? Huh? Like an ideal gas, right? At very, very high temperature, density becomes very low, you become an ideal gas. So at very high temperature, it's going to look like, it doesn't go negative, but it becomes closer and closer to an ideal gas. That's fine. And many of you stopped at it and you really did not think carefully about what happens at low temperature. As temperature goes to 0, which term of the van der Waals equation of state will dominate? The second term, right? It's only attractive forces. As you go to T is equal to 0, the van der Waals gas is a bizarre gas where it becomes a clump, right? Because there is only attractive forces. There is nothing else. As you increase the temperature, this term starts to dominate. It starts to show up, right? And that's the repulsive part. That is telling you, let's go away a little bit. And as the temperature becomes higher, this term's contribution increases more and more. So what does it tell us about thermal expansion intuitively? As the temperature becomes more, the repulsive part starts to dominate more and more and more and more, right? So you're going to see a behavior like this. So in the middle, it's going to be, so van der Waals gas actually shows a phase transition of sorts, which you don't get in an ideal gas, which is super cool. So if you plotted the derivative of this thing, you can pick your homework and over here. So my intuitive argument did not really explain why this should be equal to 0, is not explained by my intuitive argument. And I don't really care about it. Those of you who have got it right, I have not cared for whether your thing went to 0 or not. What I wanted to see was a little hump in the middle, because as you are at, and I think it's kind of beautiful that as you are at T equal to 0, only this term dominates. So it's only attractive forces. And the repulsive part increases in contribution as T goes up, right? Intuitively. You could, some of you did it through the algebra, maybe 2 or 3 of you, but a lot of people did not get this one correct. A lot of people also made mistake in the second problem. No one made mistake in the first problem, which is writing a name. But second problem, temperature stays constant. Why? It's a tricky one. It's a sneaky one. So second problem, almost everyone got P2 by P1 or P1 by P2 is equal to 5. You can pick up your homework in midterm. But then you went and did the same thing for temperature. But this is free expansion. Free expansion means expanding into vacuum, reversible or irreversible, right? There is vacuum. What is the external pressure? 0. It's free expansion. So we always have delta U is equal to delta Q plus delta W. You have been told that it's adiabatic, therefore this is equal to 0. And you know it's free expansion, therefore this is equal to 0. Therefore delta U is equal to 0. At the same time, you know it's an ideal gas. For an ideal gas, du is equal to Cv dt. Therefore temperature stays constant. This is kind of nice. Okay, so this was good. And again, if you have not scored well on the midterm, don't be disheartened, okay? You can still get a solid B+. If you have scored very poorly on the midterm, you're not getting an A. You can still get a solid B+ if you come talk to me and work over homeworks and things like that. One of your homework is going to get removed anyway. I'm willing to give you, I would be very happy giving everyone an A if you meet my criteria, okay? So please come talk to me. If you want to put in extra work, if you want to learn, I will give you extra homework and stuff and kind of, you know, this, you're all PhD students. It's not a competition, okay? Except one, you're all PhD students. So he has no competition because there is no other undergrad semester. It's fine. It's you know, so what else did I want to say? Yeah, so the van der Waals gas was the one where I did not see really an intuitive proof, which made me a bit disappointed. Apart from that, final problem, I mean, I gave bonus points to anyone who wrote anything. Some people got a few more bonus points. Some people, a lot of you attached thick papers. I mean, that's fine. You got some bonus points. What else? Any questions about it? Yeah, go ahead, Sophia.
Why, for question 2 for E, explain that the process is not reversible?
Question 2, part what?
E,
Because the delta S is positive, the entropy goes up. Even though the heat change is 0, that does not mean the entropy change is 0, right? ds is equal to delta Q by T only for reversible process. So it is a process where dq is equal to 0. That does not mean ds is equal to 0, right? I will post solutions, so don't worry. Okay, I will post solutions to this, which is probably going to be a collection of screenshots from people who got it right. So I will take permission before taking your screenshots and remove your name. Okay, I will post solutions to the midterm. Okay, let's get started.
Professor Tiwari,
Yeah, go ahead.
for the alpha part, why are you using the expression of pressure? I mean, you should, it's alpha versus T, right? Like,
Yeah,
I
I'm giving you intuition here. I'm not saying this is the right proof. I was telling you why I got excited about this problem. If I look at it, and if I got an answer, why is it that the answer that most of you drew is this should not make sense from an intuitive reason if you look at the equation of state? That's my point, okay?
Okay, fine.
I'm not deriving alpha, but I'm looking at this and saying that at 0 temperature, it's only repulsive. As the temperature increases, this attractive force starts to act more and more and more. Sorry, the repulsive force starts to act more and more and more. So that's why the thermal expansion increases as a function of temperature.
Okay.
But the true answer, which 4 or 5 of you wrote, is through the algebra, which is fine. Okay, so this was you're correct. This is not a proof. This was just to give you intuition. Okay, and I will post the solutions to this thing. So the second midterm will also be take home. It will be, you will get slightly less time. It will be similar complexity. Maybe a bit less algebra, a bit more intuitive because it will cover some more topics. Final will be in class. Okay. So thermodynamics is easy, but it's a lot of work. Okay. It's not a class where you just like, you can't sleep through it. And again, if for the final time, if you're worried about your grades, please send me an email. Let's meet, let's talk together, or a Slack message and discuss what we can do to help. So today we are going to talk about something known as Gibbs phase rule, which is really the starting point to talk about phase diagrams. Okay, and Gibbs, I'm going to state the Gibbs phase rule, and then we will work through its proof. So this is number of components. C is equal to number of components. P is equal to number of phases. 2 is a number. I don't have to tell you what 2 is. And this F is the number of degrees of freedom in a system. So let's take a little bit to understand what it is. Number of degrees of freedom. I wanted to mention one more problem from the third homework. Carnot cycle in a PT diagram. That one's also a bit sneaky. Some of you got the curvature wrong. Okay, so if I can, so it's, and I will post the answer probably to that one also. If you look at PT, you can see that it's going to look something like this. This one, and so as opposed to looking like this. So this is wrong, and this is correct. Okay, that was a bit sneaky. ST almost everyone got wrong, right, because it looks like a box, right? Okay. And actually, one of you wrote the equations are trivial. I'm not going to derive them. I deducted points. No, that was the whole point. You can't pull a trivial one on me. There's that joke about 2 mathematicians, you know, they fight for 1.5 hours or something, and then they say, oh, yes, it's trivial. Because they, yeah, anyway. So this is number of degrees of freedom. What do I mean by that? This is equal to pressure or temperature or mole fractions of different phases that can be independently varied. Okay. So effectively, all of these are all intensive variables, right? Mole fraction is an intensive variable, pressure is an intensive variable, temperature is an intensive variable. And I wrote mole fractions in all different phases because if you have 5 component system, right? So for example, if you have a system made up of iron, carbon, hydrogen, oxygen, right? So you would have mole fraction of iron, X1, X2, X3, X4. But this is not the only parameter that you can vary. If you know that the system exists in 4 different phases, then you have to think about mole fraction in phase 1. So X11, X21, X31, X41. Mole fraction in phase 2, X12, X22, X32, X42, ... So different phases, okay? So this plus pressure and temperature, these are the degrees of freedom that we can vary. And basically, this is why we defined our components in the bizarre way, which made Kinjal very, very sad. He still looks sad because of that. Remember, when we defined components, we subtracted out the number of constraints that we have, right? If you had not done that, the definition of F would have changed. That was the only thing. So Gibbs phase rule is simple, it's just super useful. And anytime you have a phase diagram, this is what really guides you in constructing phase diagrams. And let's try to work through it as to where it comes from. So we will work through the derivation today, and that will give you intuition for where it's going to come from. Okay, so let's derive this. Let me take my chair. No, this is terrible. Anyway, I ran 11 miles in the morning. My legs are a bit tired. That's okay. So let's start with first case, one component system. Okay, life is very simple, only one component. So this means we are talking about C is equal to 1. So we would like to prove, so one component system could be pure water, for example. There is no hydrolysis going on, nothing is happening. Okay, we would like to prove that F is equal to 1 minus P plus 2, or F is equal to 3 minus P, right? That's what we would like to prove. How do we prove this? Let's go even more. This was a case. Now let's look at a sub case, which is number of phases equal to 1, or P is equal to 1. So we have a one component system with only one phase. So if you think about all these degrees of freedom that I wrote over here, how many can you vary independently? You can vary pressure, you can vary temperature. Do you have any control on any of the mole fractions? You don't. It's a one component system. Mole fraction is equal to 1, and there is one phase on top of that, right? So F is equal to 2, only pressure and temperature. And 2 is indeed equal to 3 minus 1, or 3 minus P. Okay, so one component system, one phase, there are 2 degrees of freedom. Okay, is that clear? This has to be clear. Everything else builds up on this type of argument. I'll give a moment. Swimming, did you pick up Vedant's thing? Okay, good. Both of them, right? Huh? What?
Did you write what's on the bottom on the next?
Yeah, I will write it again. That's good. So we are talking about one component, one phase. Okay, so C is equal to 1, P is equal to 1. We can vary both pressure and temperature. Why can we vary both pressure and temperature? Because there is no constraint telling us that they are connected in any way. Okay, we can vary both of them independently. Just like water, when water is single component, water exists as a single component, not just, you can independently vary the pressure, right? You can take your, when you go hiking, you take your water from sea level to the top of a mountain, right? It still says liquid water. And suddenly it becomes hot, it still says liquid water, right? So you can vary pressure and temperature independently. Therefore, F is equal to 2, and there is no mole fraction to be varied because it's a single component system, which is equal to 3 minus 1, right? Or 3 minus P. So for single component, one phase, we have just shown that indeed F is equal to C minus P plus 2, right? So let's build up on this. We are still working with one component, but now let's add two phases. One component, two phases. Okay, so now we have C is equal to 1 and P is equal to 2. And what would we like to show? We would like to show F is equal to C minus P plus 2, or 1 minus 2 plus 2 is equal to 1. So we want to show that we have one component but two phases. Suddenly the number of degrees of freedom drops down by 1. So there is something that is telling you that you cannot vary both pressure and temperature independently. What is that thing? Any ideas? Where is this constraint coming from? It's like an additional constraint showed up. Go ahead.
Would be the phase barrier between one of these two phases?
So they are in equilibrium, right? If you had two phases out of equilibrium, none of this applies, right? The whole concept of phase diagram breaks away. It's purely for equilibrium systems. And under equilibrium, when you have two phases, last time we derived an equation, their chemical potentials must be same, right? Across the boundary. Or their Gibbs free energy per mole must be same, right? That's the condition for equilibrium. So at any given pressure and temperature, okay? So what it means that if two phases, alpha and beta, let's call them, are in equilibrium, then their chemical potentials must be equal. Okay. Chemical potential is Gibbs free energy per mole, right? What are the natural variables for Gibbs free energy? Anyone remembers? P, T, and N, right? And you're talking about per mole, so you can ignore the N, okay? So we can say mu for phase alpha as a function of pressure and temperature must be equal to mu of phase beta as a function of pressure and temperature. And I did not write N over here. So why did this happen? This statement happened because mu is equal to G by N and G is equal to G of P, T, N. Those are the natural variables for G, right? That's where it comes from. So the chemical potential must be equal, and chemical potential is a function of pressure and temperature. So you suddenly have a constraint. Anytime you have such an equation, it's forcing you that not all values, you don't know what exactly is mu. You don't care for that, right? All you know is that some function of pressure and temperature is equal to some other function of pressure and temperature. So you have one equation in two variables, right? So that means only one of them can be varied independently, right? In other words, you had two things. So the total number of degrees of freedom is always pressure, temperature, and mole fraction in every component, okay? Mole fraction of every component in every phase. Here, there is only one component, so we don't care about mole fraction, leaves pressure and temperature. On top of that, you have one constraint. Therefore, number of degrees of freedom is reduced by 1 due to presence of one constraint, which is this equation. Okay, so therefore F is equal to 1, which is once again C minus P plus 2, because we had one component, we had two phases, and 1 minus 2 plus 2. Okay. Okay, let's keep building.
Where are we? I didn't understand where this equilibrium thing comes from. Like,
wait, we're talking about equilibrium phase diagrams. That's where it comes from.
But nowhere in the like phase rule or in the definition of components, other than when we explicitly talked about equilibrium for the.
Here, this should make you happy. Better?
Okay, and then I had one more question about the component thing itself.
Mhm.
So we define it as number of chemical, like we subtract the number of chemical reactions happening. So for a truly reversible reaction, do we consider that as two reactions or one reaction in our system? Because you have a forward and a backward reaction, right?
It's one reaction.
Okay.
Good. Yeah, these are equilibrium phase diagrams. This is equilibrium thermodynamics. This whole semester, we will have conditions to say which is the direction of spontaneity, but phase diagrams, we are focused entirely on equilibrium. Okay, good. So now let's go one step further. Yeah, good question. So one component, three phases. Okay, let's call these phases alpha, beta, gamma. Now, how many constraints will we have? We will know. What do you mean zero? Degrees of freedom might be zero. I'm asking about constraints. So we will again have mu of alpha at pt is equal to mu of beta at pt. So three phases are existing in equilibrium. It's like the triple point of water because it's a one component system. Mu of gamma pt. So trick question, how many constraints is this? Michaela, what do you think? Two or three is your answer choice. Now, how many equal signs do you see?
I'll take two. Yeah.
Because if it's you're saying mu alpha is equal to mu beta is equal to mu gamma, that already captures that mu alpha is equal to mu gamma, right? There is not a third thing. That's why I said it's a trick one. So there are two constraints, and you were starting from 2 degrees of freedom, and now you have added two constraints because you have two variables, pressure and temperature, and you have two different equations. So when you solve for them, you will get a number, you will get a unique value of a pressure and temperature which can satisfy this. The equation might be very complicated. You have to go and measure how your mu will depend on pressure and temperature. That's another story. But at best, you can have one value of the answer. Therefore, so this means two equations in two variables, P and T. Therefore, only one solution. You cannot vary anything independently. There will be one unique value of pressure and temperature. And when you have one data point, there is no degree of freedom. There is no freedom. There is just one value that you can take. Therefore, F is equal to 0. Once again, that is equal to C minus P plus 2 because we have 1 minus P, 3 phases plus 2, right? So we again got one component, 3 phases gives us 0 degrees of freedom. Okay. So if for a single component system, you have 3 phases coexisting, you cannot vary pressure and temperature independently. Let's push it one step further. Can we have one component system with 4 phases? Why, Aiden?
Because you said so last time.
And now, as per this superior argument,
Yeah, that's your argument.
negative F does not mean anything. There is no possible pressure or temperature which will do it, right? You have an over-constrained system. Let me write it down carefully here. One component, 4 phases. Let's call it alpha, beta, gamma, delta, right? So now we will have mu alpha pressure temperature as a function of pressure temperature is equal to mu beta as a function of pressure temperature is equal to mu gamma as a function of pressure temperature is equal to mu delta as a function of pressure temperature. So 3 equal signs, right? 3 equations. 3 equations in 2 variables, pressure and temperature, which is bad news. Okay, you can't have a solution. F becomes 2 minus 3 is equal to minus 1. Simply not possible. So that's why in water, pure water, you have a triple point. You don't have a quadruple point. Now, if you have water mixed with something else, if you have a 2-component water, a solution with salt or something like that, then you can have 4 phases coexisting, right? Because then the C comes and helps you. So this is all a bit abstract, but this becomes very practical. let's try to construct a fake phase diagram in pressure temperature space for a single component system. Okay, so what I want to do is to think about, I will draw a diagram, then I want you to work with me carefully and mark regions, and some of the diagram is wrong and you have to tell me which one is wrong. Okay, so let me just draw it. It's purely fake. There is no such system which has such a phase diagram. Yeah, so this is a one component system. And let's start with this region. How many phases could exist in this red region? This is a one component system, and the red region, what does that mean about degrees of freedom? Huh? 2 degrees of freedom. And for one component system, what was the value of P for which we got F is equal to 2? One phase, remember? F is equal to 2 was obtained for one component, one phase. Okay, so when you can vary both pressure and temperature, that is going to be a single phase region. Okay, so this is, let's say, phase alpha. So we have F is equal to 2 and P is equal to 1. Similarly, this region that you have over here is going to be some other phase. Let's call it phase epsilon. Let's call this one as phase beta. So all these areas in a phase diagram, in a pressure temperature phase diagram, yeah, just one moment. Yeah, actually, go ahead.
Can you repeat, why did you get F equal to 2?
Because I shaded an area. So when I shaded an area, it means I can change my pressure independently of temperature. I can change my temperature independently of pressure. Yeah, it's an area, right? Area means 2 degrees of freedom. So this is phase beta in the middle. I'm just giving it names. Let's say this is phase gamma, but the point being that all of these are going to be single phase regions. Okay. Now let's think about the boundary between this one. What are the number of degrees of freedom along this boundary? Why? No, but degrees of freedom. Can you vary pressure and temperature independently along this curve? Right? Anytime you know the value of pressure, you know the value of temperature. You cannot vary it independently. And if you go back to the list we went through, when we had F is equal to 1, that corresponded to 2 phases, right? So that's coexistence. So this boundary between alpha and gamma is the boundary at which both alpha and gamma coexist. Okay?
Just a clarification, this is a one component system.
Yeah, one component. Yeah, everything for one component. We'll do enough 2 component, don't worry. We'll do 3 component also. It's known as Gibbs triangle. We won't do quaternary. Okay. How about this one? Same idea, right? It's again boundary between 2 phases, 1 degree of freedom. You cannot vary pressure and temperature independently. Anytime you have pressure, you have value of temperature. So this is going to be what 2 phases should exist along this line. So I mean, the line between gamma and epsilon. What 2 phases should exist along this line? Gamma plus epsilon. Good. So, and this one is going to be beta plus epsilon. This one is going to be alpha plus delta. This one is going to be epsilon plus delta. This one is going to be beta plus gamma, so on and so forth, right? So any curve in this one component system is a 2-phase region.
Sorry, isn't it supposed to be beta plus delta, not beta plus epsilon?
You know what I mean? Yeah. If I write too much, I make mistakes. Beta plus delta. Good. So now let's think about this point. How many degrees of freedom? 0. Right? There is no freedom. There's a point. You're stuck there. 1 degree of freedom corresponds to, no, 0 degree of freedom, F is equal to 0, corresponding to 3 phases coexisting, right? So what are going to be those three phases? This is happy marriage between alpha, beta, and gamma, right? So this point is a triple point. Alpha, beta, and gamma. Similarly, this is a triple point. Alpha, beta, and delta. How about this one? Is this possible? How many phases do I have there? 4. Beta, gamma, epsilon, and delta. That's simply not possible because the number of degrees of freedom is not 0 for that one. It's -1. You cannot have a solution. You might have some very lucky special case where those equations have some redundancy and you get a solution, but basically it's not going to happen. So this is not possible. So next time you're doing your research and you see a phase diagram with a quadruple point in a single component system, you immediately know those people are full of crap. Okay, there's some mistake. You can decline, you can reject the paper. However, if you had a 2-component system, then you could have it. You could have a quadruple point in a 2-component system. In a 2-component system, you cannot have a pentuple point. You need to go to a 3-component system, so on and so forth.
So we can't have a technically a point there, right?
It's not possible. This phase diagram is wrong. Most likely it was not in equilibrium. Most likely there were some time-dependent features going on. You have not really let your system relax.
But if I just remove the point and then the diagram is possible.
Yeah, sure, but I will have to re-level everything, right?
Because only one point is not allowed.
Sure, if I was to remove the point and if I learned that beta and delta are actually the same phases, then this disappears, right? Then it's okay. You can do 50 different things, you know.
But I can have a line between beta and delta without the line joining the other lines. Means point of discontinuity.
What do you come here and do it? You're making me be all drawing was never my strong. What are you talking about? Come here, draw it.
So just I am saying that
Come to the iPad. Here you go. Draw. Not your finger.
Yeah, you just remove this point.
Do it. What's the meaning of that? That doesn't mean anything, right? Now the reason that doesn't mean anything because you remove that. Now you have this area. Thank you, by the way, for coming here. This area that you suddenly vanished, it's a 2-degree of freedom area. And now you're telling me that maybe beta, epsilon, gamma, delta, everything exists over there. You cannot have a 2-degree of freedom area with 5 different phases, right? So you cannot have lines just dropping off in the middle of nowhere, except when it's a critical point. That's the only time we will talk about critical points and van der Waals will come back. Okay, does it make sense? Yeah.
Beta and delta line in M. And then you said that beta and delta were the same phase. And the line, it kind of goes back on itself. You can't have a line.
Yeah, you could have 50 different things. I was kind of coerced into deleting that line by Kinjal. So talk to Kinjal. I don't want to delete that line. This is a toy phase diagram. Okay, you could break it in 50 different ways. Okay, that's the point. But you cannot have. So what Kinjal did was a good exercise because it shows us what we cannot do. You cannot just delete this region because then how many phases do you have there? You cannot have 5 phases with 2 degrees of freedom in a 1-component system, right? So this F, it's possible. It's very likely you will forget the derivation, and that's okay. Keep the gist of it at heart. How did we start? We started by imposing chemical potentials as constraints, and then we worked our way from there. What you should not forget is F is equal to C minus P plus 2. Now, certain books will show the Gibbs phase rule as F is equal to C minus P plus 1. Certain books will show you that F is equal to C minus P plus 3, depending on how they deal with pressure and temperature, and that becomes a whole mess. I'm going to just follow F is equal to C minus P plus 2. Basic idea is the same. Good. Any more questions? And last phase diagram destruction, Kinjal? No? Okay, let's go further. Okay, so we derived F is equal to C minus P plus 2 for a 1-component system. We did not derive it for a multi-component system. I want to do it for a multi-component system. And it's the same idea. The math will look just slightly gnarlier, but it's the same idea. So let's work through it. So we had case 1, which was 1 component, case 2, and we won't do 2-component and 3-component separately. We are just going to jump to another case. And I think this serves a purpose. That's how I'm going to do it. More than one components. So C is more than one, some large number. So now let's count the total possible number of degrees of freedom. So we have more than one component and P phases, okay, where P can be 1, 2, 3, 4, whatever you want. Okay, we are going to consider the most general case. Let's count the total possible number, total possible degrees of freedom in such a system without worrying about constraints or anything like that. How do we count it? What are the first two that come to mind? Pressure and temperature, right? So pressure, temperature. What else? Mole fractions. How do we think about mole fractions now? Who wants to help me? Go ahead.
Number of phases by number of components.
Let's start together. Let's work carefully. So let's say we have component number 1, x1. So mole fraction of component number 1, mole fraction of component number 2, mole fraction of component number 3, till mole fraction of component number C, right? And let's say for now, if there is just one phase, okay? Does this mean we have capital C number of degrees of freedom on top of pressure and temperature? Why not? You're nodding your head. Is there a constraint here on these mole fractions? How many mole fractions can you vary independently for any system?
N-1.
Yeah, he's on Zoom. He's like voice of God today. Yes, you are correct. This has to sum up to equal to 1, right? So you have C minus 1 degree of freedom due to Vedant.
Yeah.
Henceforth, you lose your speaking rights.
Oh,
I mean, you have questioning rights, but you don't get to answer any questions, okay?
okay.
Yeah, it was not for you, but that's fine. I will come to you if it's needed. So yeah, you can relax. So we have C minus 1 degrees of freedom. This is for one phase, right? Now let's say you have P phases, and this degrees of freedom, these mole fractions will exist independently for every phase, right? So now we will start thinking about phase number 1. All of this applies to, I put a little superscript and say this is for phase 1. Let's go to phase 2. Phase 2 will also have a similar relation, x1 superscript 2, x2 superscript 2, x3 superscript 2 plus xc superscript 2 is equal to 1. So again, C minus 1 degrees of freedom. And if you went to phase P, the final phase, you will have x1 phase P superscript x2 superscript P plus xc superscript P is equal to 1. Again, C minus 1 degrees of freedom. So how many degrees of freedom did we get in total? Pressure plus temperature was 2. And now we have capital P multiplied by C minus 1, right? This is the total possible number of degrees of freedom you can have. We haven't quite yet done Gibbs phase rule, but we are almost getting there, okay? And notice, so this is like a matrix where the rows sum up to 1. You don't have any restriction on the column summing up to 1, right? The mole fractions can vary wildly. There is across phases. There is no restriction on that, okay? It's only in this direction that you have a constraint. So this is the total possible number of degrees of freedom. So if we were to just think of this as F, what would we get? We would get F is equal to 2 plus PC minus P. That doesn't look like our Gibbs phase rule, right? This is PC. We would get F is equal to PC minus P plus 2. But our Gibbs phase rule is F is equal to C minus P plus 2. So we haven't subtracted out the number of constraints yet, right? So we need to write down the number of constraints, just like we did it for the previous problem, equating the chemical potential, okay? So, and then we will find out that it works out nicely. This ignores constraints due to chemical potential. Okay. So how do we write that now? Same thing like we did last time. Mu of phase alpha at a certain pressure and temperature is equal to mu of phase beta at a certain pressure and temperature, dot, 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 up to mu of phase P at a certain pressure and temperature. How many equations is this? As Michaela told us last time, you have to count the number of equal signs, right? So you have P minus 1 equal signs. Okay, if you had only two phases, it would have been one equation, right? If you have three phases, it would have been two equations. If you have P phases, it is P minus 1 equation. So this is P minus 1 constraints. But note, we are not working with a one component system. We are working with a C component system, right? So just like we did last time, now we have to put back our subscript here corresponding for the number of components. So this is for component number 1, component number 2, and goes up to, sorry, we are doing it for component 1. So all of this is for component number 1. We will have a similar equation for component number C, the last one, and all the ones in middle. Component number C will also have mu C of alpha PT is equal to mu C of beta PT dot, dot, dot is equal to mu C of phase P at P comma temperature. So P minus 1 constraint for each component, and how many components? C. So total number of constraints is equal to C multiplied by P minus 1. Total possible number of degrees of freedom was PC minus P plus 2. So let's call this equation number 1. Let's call this equation number 2. Equation 1 said F without constraints is equal to PC minus P plus 2. Subtract 2 from 1 to get F is equal to PC minus P plus 2, and we subtract this thing over here, minus C, P minus 1. What do we get? PC minus P plus 2 minus PC plus C, or C minus P plus 2, because PC and PC cancel, and you get C minus P plus 2. So we have derived the Gibbs phase rule for a very general multiple component, multiple phase system. Okay. Again, the derivation is not that complicated. It's just counting number of equations and number of variables you have. If you forget to the mechanics of the derivation, that's okay. I don't care. You should not forget the Gibbs phase rule. It's important. It's very important. Any questions about this?
I have a question. What
Yeah,
is so going back to that phase diagram you drew? I mean, not exactly that, but when you say that mu is equal for all phases at a pressure and temperature, what does that like how do you indicate that on the diagram? And that's something
At this pressure and temperature, mu alpha is equal to mu delta. At this pressure and temperature, mu beta is equal to mu gamma. At this pressure and temperature, mu gamma is equal to mu epsilon. That's why they can coexist.
but no, in your notation, you have PNT the same for all phases and all this thing.
No, I am writing it as a function of pressure and temperature at a
Oh,
given
yeah. Okay. Sorry.
variable. No, don't be
Great.
sorry.
I got it.
Good. So, yeah, this was a dense class. I don't want to add a new topic here. And it's important that you go and assimilate what we have done. But I want to ask you a question, which we will answer next time. I do it in my undergrad class also. So, JP, you're not allowed to answer. Okay, good. So, who here knows how to ice skate? Raise your hand. Good. I'm terrible at it. So, Sophia, how do you think ice skating works?
I know exactly what you're gonna ask.
That's okay. You are not allowed to answer.
Yeah.
Or anyone, how does ice skating work?
It's a blade.
It's a blade.
than
Yeah.
point, and the ice. I don't know, I guess it's like two hard surfaces that don't.
So it looks like it probably melts the ice locally, right? That's the thing that we think of, right? That you apply pressure. And if we think about, so let me set it up for next time. Also, by the way, I know how ice skating works, but it doesn't mean I can ice skate. I'm terrible at it. So that's. So if you think about the pressure of the phase diagram of water, that looks something like, and now you can, actually, this is a good point to think about the phase diagram of water in light of what we just did. So in the phase diagram of water, this is liquid, this is vapor, and along this line, liquid plus vapor can coexist, okay? Which is something we know, right? When the water is boiling, sometimes you have liquid and vapor at the same time, right? It's not all become steam. And this is solid. So the argument that we normally think about ice skating is that, so this is triple point at which three phases can exist. And here you actually have a Kinjal situation, okay, where it stops, the line actually stops. And that's a very special point. It is known as the critical point. We will talk about critical point a bit later. But you cannot have a quadruple point in water, in a single component water. So the idea is that as ice skating doesn't happen in summer, right? It happens in a cold temperature. And I mean, when I was a grad student in Pasadena, they had a skating rink in Pasadena in like 90 Fahrenheit, because the skating rink itself was very, very cold, right? So you go to a very low temperature. Does anyone know what is the typical temperature of an ice skating rink? It's around like 25 Fahrenheit, right? It's a bit, or 20 Fahrenheit, it's in that regime, -5, -6 degrees Celsius. So if you go to a low enough temperature, which means you are moving in this direction, right? You're decreasing your temperature. And you are in this part of the phase diagram, you want to go over here, right? Because you cannot really skate on liquid. That will look funky, right? So let's say you are at a particular temperature, and let's say this temperature is T is equal to, we are all physicists and chemists, we won't use this stupid Fahrenheit scale, we will say -5 degrees Celsius, okay? If this is -5 degrees Celsius and you are liquid, how is ice skating going to work? You want to apply no, let's think of it slightly another way. So I want to set up the localized melting argument and then next time work through as to why it's actually incorrect. So let's say we are at a cold enough temperature at which you have only solid. So let's say this is T is equal to -5 degrees Celsius. It's only solid, and you cannot skate only on solid also, right? Because that's, I mean, you will slip on it, you will fall, you will get hurt, but you cannot, why should your blades move, right? So if the localized melting argument is correct, what you're going to do now is to apply some pressure to it, right? By having very, very sharp blades so that it goes and comes to this point over here. So you keep the same temperature and you apply pressure. Once you apply pressure, you go from all solid to solid plus liquid. And maybe a tiny veneer of water appears on the top of ice, right? And maybe you can skate on that. Next time we will show that this amount of pressure that you need to apply for ice skating to work is actually so high that is simply not possible. I won't tell you how it works. I will share some links. Maybe Nathan knows how it works. I will share some links. People are still fighting over it. Actually, there is some nanofilm of water that forms, and not due to localized melting. People are actually still arguing over how ice skating works, believe it or not. I have a friend, David Limmer at Berkeley, and he had an article in like, it was not Vogue, but one of those magazines, you know, where you don't expect a science article saying that we still don't understand how ice skating really works. People still argue over it. So, and for this, even for this to work, this slope should have been facing the left side, right? Imagine if water was one of those things where the slope of the solid liquid line was facing this way. then it would be totally out of the question, right? So next time we will start working, it's not just about ice skating, we will start working on how to characterize these curves, how to characterize the curve along which two phases coexist. Can we write down the equation for such a curve? Okay, how do we characterize such a curve? What can we do with it? So that leads us to something known as Clausius equation and Clausius-Clapeyron equation. So we'll work with those. Any questions?
I have a question.
Hmm?
Does the Gibbs phase rule tell us the number of the maximum number of phases that can possibly coexist, or does it tell us that we have to have this point? So for our one component system, like water, for example, does it tell us that we have to have a triple point, or
Yeah,
it just tells us that?
it's an equality. It's not an inequality, right?
Hmm.
It's telling you P is equal to F, P is equal to C minus F plus 2. It's not telling you P is less than equal to or P is more than equal to. It's an equality. So yes, it
Okay.
does. And this is important.
Okay, thank you.
Okay, good. So look through your midterms and everything. And again, I'm in very lenient. If you think I've still cut marks very unfairly, please write to me and I'll try to give you. But then I've been very lenient in general. So, and if you're unhappy about your midterm, if you're worried about the course, please write to me separately and we will